All right. Hello, everyone. Welcome to your next online class. We're talking about space science today. And as I promised last week, we're going to be talking about what does it take to get to Mars. It's not easy, which is why it's really interesting. So how to get to Mars. Those are the words that are on the screen right now. I have a new background. There we go. Green screen. It's only green surface behind me. I can't see it right there, so I have to look at the screen. This is the comet Neowise, which we've talked about at the start of each of the last several space science classes. This particular photo of this comet was taken by my friend Chris, who works here at Delphian. This is a view of the comet from the Delphian school soccer field a few nights ago. So I loved it. It's going to sit there and join us on our journey as we learn about how to get to Mars. Okay, a bunch of people in here saying hello and good morning. Tanisha says, for the past few days, me and my family have tried seeing the Neowise comet, but we had no luck. Do you have any suggestions on when, where, and how to find it? Okay, here is what I have been able to figure out so far. Do try to see it in the next few nights. It appears that the comet is getting a little bit more faint each night. It is moving away from the sun, and the farther away from the sun it gets, the less reflective it's going to be, and the less easy it's going to be able to see with your own eyes. If you have a pair of binoculars, or even better, a telescope, you're going to still be able to see it really, really well. I saw it with my own eyes last night. It's just a little bit fainter. We're kind of north in the United States here. So if you're at the same latitude as us, Oregon or Idaho, Michigan, New York or New England on the East Coast, about 10:30, 10:45 is when the best viewing time that I've found is. I look to the northwest about 10:45, and you'll see it. There's about 2 hand spans up in the air from the horizon at that time. Let's say you're not a night owl. You don't like staying up late, but you have no problem waking up early. About 5 a.m. is when I've heard. I'm never up at 5 a.m., so I don't know this. But 5 a.m., look to the northeast. Look towards where the sun is going to rise. The comet will be up, but not the sun. The sky will still be dark, and you should be able to see it there. I hope you're able to see it with your own eyes, Tanisha. And if not, don't worry. This comet is on a regular orbit. It will be back in 6,800 years. You can catch it then. I am no help at all. Okay. Hello to California and to Pakistan and to everywhere else that people are joining us from. If you don't have binoculars or a telescope, you can still see it with your own eyes if you're in an area without light pollution. If you live inside a city, take a field trip, talk to your parents and, go driving out of the city so there's not a lot of light pollution happening. If you can see the Milky Way, sorry, not the Milky Way, if you can see the Big Dipper constellation clearly and easily without too much squinting and stuff, you should be in an area that's dark enough to still see the comet. We'll see. I'm watching it every single night. It gets a little bit fainter every night. Well, we are going to learn about something that the comet will never be able to do, which is land on Mars. There's a few different steps to land on Mars. Before you get to Mars, you got to take off from Earth. And then from Earth, you got to actually go over to a different planet. And then you need to figure out how to get from around the planet to on that planet without crashing and exploding. Each of those things are difficult. Let's learn about that. By difficult, I mean awesome and fun. So here is just a lovely graphic. I just started Googling Earth to Mars, and I love this graphic. It shows, here's the Earth here. We have the moon there. It shows us taking off and going past the moon, heading to Mars. I don't know what all these lines are, but I thought it looked really cool. All right. There are options for how to get off of Earth. If you were following my Instagram stories yesterday, I posted a little picture and asked if you could identify the rocket that I just showed, this part of the rocket right here. And a few people were able to figure out, and they said, that is an Atlas V rocket. Yes, absolutely correct. Here are the three main options available to you right now to get off planet and to go to Mars. I wouldn't ride in one of these right now. We don't have human rated vehicles yet, but let's say you wanted to send a payload. You wanted to send a rover or a satellite over to Mars. These are your three main options right now. The Atlas V rocket is the most experienced rocket that we have right now with getting something off planet to Mars. The Delta Heavy is another great option. The Delta IV Heavy, and the Falcon Heavy is a new entrant into this field. We haven't sent anything to Mars on the Falcon Heavy yet, but it's definitely an option. There's strengths and weaknesses to each one. The Atlas V, it costs about $110 million per launch, which is actually pretty good for rocket launches. The amount of payload that I put here, this is how much this rocket can get to low Earth orbit, which is not very far away. It's just a couple hundred, 200-300 miles up from the ground. Low Earth orbit is where the International Space Station lives. It's where a lot of our satellites live. But it's a good number to look at when figuring out how powerful is a rocket and how much cargo can it get up. So the Atlas V costs $110 million per launch. It can get about 45,000 pounds of stuff up into low Earth orbit, which gives you a cost per pound, which is a very, very useful number when looking at in space launches. Cost per pound of about $2,400. That's not bad. The first shuttles, the first space shuttle launches that we sent up, the cost was about $25,000 per pound of cargo, per pound of payload to get into low Earth orbit. So the cost has gone way, 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 way down. If you're trying to launch something bigger and heavier, so you need to launch something that's a good 50% heavier than what you were putting in the Atlas V rocket, your Delta IV Heavy rocket is a good option for that. It costs more. It costs $350 million per launch. So that's, I don't got that kind of money. But it can send over 63,000 pounds of stuff into low Earth orbit. So it's more costly per pound. It's about $5,500 per pound. But if you need to launch something bigger than the Atlas V can carry, Delta IV Heavy is the way to go. Both of those rockets have launched things that have gone to Mars. The Falcon Heavy looks like a good in-between. It costs $150 million, so much less than the Delta IV Heavy and a bit more than the Atlas V rocket. But look at how much it can send up. It can get 140,000 pounds to low Earth orbit. That is more than twice as much as the Delta IV Heavy and way more than the Atlas V. And the cost per pound to low Earth orbit with the Falcon Heavy is just over $1,000. That is really cheap when it comes to rocket launches. Again, the space shuttle was $25,000 per pound to get something into low Earth orbit. Okay, I'm gonna hop into the Q&A section. A lot of numbers there. I hope I am not leaving all of you with your head spinning with numbers here, but it's space science. We're gonna get technical. Okay, good. All right, a bunch of people just saying hi in the Q&A section. So hello to everyone. All right, so we got off planet. We are now in orbit around the Earth. Here's a gorgeous real picture of the International Space Station coming, probably coming over the horizon towards the sun, achieving sunrise. And this thing orbits the Earth every 90 minutes. So this amazing visual of, here they are seeing the sunrise. In an hour and a half, they're going to see another sunrise. And another hour and a half after that, another sunrise. Every 90 minutes. So how do you get from Earth to Mars? You just got, let's say that we were launching on, oops, I'm going to go back here. Let's say we launched on the Atlas V. The Atlas V is what launched the Curiosity rover that landed on Mars in 2012. It's what's launching the next Mars rover that is launching in probably just a few weeks, the Mars Perseverance rover that's launching on an Atlas V. So let's say we launch in an Atlas V. We've got our, 45,000 pounds in low Earth orbit or something like that, right? Well, you need to get from here to there. This guy, Walter Homan, he was a German physicist, German engineer, German space guy. He lived from 1880 to 1945, and he figured out that there was a smart way to go from one planet to another. So let's take this diagram here. Let's look at orbit 1 and orbit 3, okay? Here's the sun in the middle. Let's say orbit 1 is the Earth, and you have the Earth orbiting here, and it's a smaller, quicker orbit. And let's say orbit 3 is Mars. So we have it blue and red. And Mars is traveling on this one over here, and it takes a longer time for it to go around. They're going to be moving at different speeds. Let's say that you insert a third orbit, orbit number 2 here, and you put your spacecraft on an orbit that's not a perfect circle, but what's called an ellipse. It's that oval shape right there. So the Earth is orbiting here in a circle, Mars is orbiting in this circle, and your spacecraft is orbiting in this ellipse here. That orbit takes you back and forth from the Earth to Mars, back and forth, if it just kept going and going. So he developed this idea, and we call it the Homan transfer orbit. It's named after this guy, Walter Homan. It's used to transfer something from one orbit to another. This could be used from Earth to Mars. This could be used from Mars to Earth. This could be used from Mars to Jupiter or Earth to Jupiter. You have any two orbits, and you can figure out how to send your spacecraft to kind of go in between the two of them. So every 26 months, the Mars and the Earth are perfectly lined up to use the Homan transfer orbit with as little extra cost, as little extra fuel as possible. Fuel is really important in space travel, in getting from one planet to another, because any fuel that you use, you need to bring with you, right? So let's say you need to burn 100 pounds of fuel in order to get from Earth to Mars. Well, guess what? Depending on what rocket you use, if you need to bring 100 pounds of fuel and you're launching on the Atlas V, you need to launch all that fuel into space, and that's going to cost $2,400 per pound of fuel. So it gets expensive quick. So if you can use the littlest amount of fuel possible, that's the best. It's going to be the cheapest. So he figured out every 26 months, the planets literally align. They are in the perfect position so that you can have the shortest, quickest engine burn to leave Earth's orbit, and then the shortest, quickest engine burn when you're approaching Mars to stop and slow down and to land on Mars. There's a handy illustration of this. So on the bottom here, on the inside here is Earth. And this is not made up, this is an exact orbit showing how the InSight lander, which is a current lander that we have on Mars, how the InSight probe, the InSight lander, got from Earth to Mars. So on the inside, you see Earth. You have the purple line, which is the InSight lander. One quick burn to leave Earth and to go towards Mars. And then as it approaches Mars, which is the green line out there, it does another engine burn to slow itself down and to come into contact with Mars. I'm going to let that run one more time. Again, only every 26 months, so every 2 years or so, are the planets in perfect alignment. You can get from Earth to Mars without using this exact plan. You can get from Earth to Mars shorter than every 26 months, but it's going to be more expensive. It's going to be more difficult. You're going to need to bring more fuel. You're going to need to be more precise in your calculations. It's just a lot easier to use this Homan transfer orbit. So doing that, it's going to take 9 months to get from here to there. And if you were to reverse that, if you were to leave Mars and come back to Earth on a very similar orbit, you just reverse it. Again, it would take about 9 months. There we go. Okay, jumping back into Q&A. Ved is asking, are space shuttles the space airplanes? Yes, the space shuttles were the ones, they would launch like a rocket. They would launch straight up, do their space stuff, and then they would come back down and land like a plane. They would land on a runway. Gorgeous machines, very complicated. We don't use them anymore. They all were taken out of service in 2011, but they were an amazing, amazing creation. All right, Alette's asking, what took that picture of the ISS that I showed a few slides ago? Probably a spacecraft that was approaching the International Space Station, probably a resupply vessel or a capsule with more crew. And as they were approaching, it looks like that's when they took that photo. All right, Tarun is asking, when is the next launching? Where's it gonna land? And okay, remind me at the end of this. I'm gonna try to pull it up and make a note here to show you a really cool website that shows every space launch that is happening. All right, Milo's saying, did you know that humans are expected to get on Mars in 2030? I really hope so. Yes, I know that that is a plan. I know that China is really trying to get humans on Mars by 2030. I know that the United States would love to get there, maybe just a little bit before China. It's a competition. It's a race. I like that kind of healthy competition. There's a lot to do before then. We haven't sent anyone to Mars yet. We're 10 years away, 9.5 years away. There's a lot of science that needs to happen between now and then to make it happen. So it's not going to be easy. If we want to get there in 2030, we need to be working our butts off right now. Okay, so now we've used that. We've launched from Earth. We have used the Homan transfer orbit to transfer from Earth over to Mars. Now we've arrived at Mars. How do you get from orbit around Mars onto the Martian surface? We're going to talk about two main approaches that have worked successfully in the past. So the first one is, and don't worry about all this stuff here. This is a general diagram showing the whole sequence. We're going to look at every step of this. Yeah, basically you come on through the atmosphere, you use a parachute to slow down, and then you're actually going to use airbags to get to the final distance and to bounce and roll to a soft, safe landing on the surface. So first is you've got your spacecraft, and it was connected to what's called the cruise stage. This is the part of the spacecraft that is meant to help your main payload, your main package, get from Earth to Mars without, running into objects in space and, to supply it power and stuff like that. But once we get to Mars, we don't need that cruise stage any longer. We don't want to bring that to the planet with us. So the landing section here is going to separate from the cruise stage. And that landing section is going to enter the Martian atmosphere going incredibly fast. And it's going to heat up super, super hot. It's very similar, basically the same thing that's happening when you enter the Earth's atmosphere. You're going, 17,000 miles an hour, 25,000 miles an hour, and you hit the atmosphere, you hit the air, and you start to slow down really fast, but it generates a lot of heat and light, as you can see there. And the spacecraft becomes a shooting star for a few minutes as it slows down. And there's a heat shield on the front end there that is specifically designed to take all of that heat and to survive that heat and to help the spacecraft inside not get cooked to a crisp, because that would be a shame. So once the atmosphere has slowed the spacecraft down, it's still going way too fast because the Martian atmosphere, it is not as thick as Earth's atmosphere. It's only 1/100th the thickness of Earth's atmosphere. So you're still going way too fast. So once you stop catching on fire from the atmosphere, it then deploys a parachute. And that parachute is going to slow it down even more, but not enough because the atmosphere is very thin. And the thicker the atmosphere, the more that parachute's going to work. The thinner the atmosphere, the less that parachute is going to work. So it slows it down some more, but not enough. Once that parachute is deployed, that heat shield is going to jettison, which means to separate from, to push away from, right? So the heat shield here is disconnected from the rest of the craft, and it falls away, crashes to the planet safely out of the way. Once that heat shield is jettisoned, the lander itself, this is the actual thing that's going to go down to the surface. It lowers down on this kind of like tether, almost bungee cord kind of thing, right? And it's going to now hang below this part of the spacecraft. So now you've got this, imagine standing on Mars, and you look up and you see this up in the sky, and you're like, what is happening up there? Aliens are invading. Earthlings are the aliens on Mars. So you've got the parachute here, dangling below the parachute, you've got the main shell of the spacecraft. Dangling below that spacecraft, you have the actual landing portion of your craft. And it starts now scanning the ground. It has radar that's scanning the ground to see what's under us, what's coming up. It will have a map of Mars in its memory. And by scanning the ground, it can now figure out where it is on the planet and figure out where it's going and figure out where this thing is going to end up landing so it can start planning for that. At this point, if they're like, oh, hey, there's a big, crater coming up and we don't want to land in the crater, we want to land before the crater, the spacecraft can do some stuff. It can guide itself a little bit in the atmosphere there to go left or right or further or not go as far to make sure that the spacecraft lands in a nice, safe place on the planet, not stuck in the bottom of a super steep crater that it won't be able to get out of. So once it starts getting low to the ground, this thing is covered in airbags, super strong material so that when it bounces onto the ground, it doesn't just break everything. So what's inside here is a very delicate rover. The slides that I'm showing you here were from the plan to land the Spirit and Opportunity rovers back in the early, when did they land? 2000s? Early 2000s, I think. And these were delicate things. You're not going to take, a hundreds of millions of dollar spacecraft and just throw it onto a planet. You're going to put airbags around it. So the airbags inflate. As it gets really low to the ground, it's now just about 40 meters above the surface. In order to slow it down even more, there's rockets on that top spacecraft thing. And those rockets are going to fire and it's going to, stop going down. It's just going to hover there. And then once it's still, it's not going left or right or up or down, it's just hanging there. At that point, the lander is cut free. It separates from the cable that was holding it, and it's going to fall the last 40 feet to the ground, right? Martian gravity is not as strong as Earth gravity. So this, depending on how it lands on the ground, this thing could bounce 40 feet back up into the air or higher. If it lands at a weird angle, it could really bounce way back up. And it's going to bounce and roll and bounce and roll, and it might roll for like a kilometer before it finally comes to a stop. It's just boing, 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 boing. We just threw a bouncy ball at Mars. That's how we have landed rovers that are worth hundreds of millions of dollars. We threw a bouncy ball at Mars and waited until it came to a stop. So finally comes to a stop there. It kind of looks like BB-8 from Star Wars. I like that. So once it's landed and come to a stop, the airbags are going to deflate and they're going to just, and this lander is going to open up. Now, depending on how it lands, there's 4 sides to this thing. they want it to open this way. So there's a way that the airbags deflate that can roll the thing into the correct, onto the correct side that they want it to open from. So the lander starts to open, and it opens the rest of the way, and nestled inside that shell and inside the airbags, you have the rover itself, which opens up, and it opens its solar panels, and it's kind of like camera telescope goes up, and this thing is ready to roll around Mars and do some science. Let me catch up with all of your questions. Juan Carlos is asking, would you like to go to Mars? Yes. I very much would like to go to Mars. Even more, I would like to come back. So there's a lot of science and engineering that needs to happen before that. So I wouldn't want to be the first guy going. I don't think I'm the best candidate. I don't have the right background. I don't have the right training. I would like someone more qualified than myself to go to Mars first. Then once they figure it all out, I definitely want to go. Okay. I'm catching up on all of your questions here. Okay. Oh, Juan Carlos with a great question here. I actually didn't cover this here, but I will. What would happen if the parachute fell? Right. So let me go back to this slide here that's showing the entire thing. So we talked about, here it is in orbit around Mars. It separates from the cruise stage. It enters the atmosphere and catches on fire, slows down a lot. Parachute deploys and parachute slows it down. Heat shield comes off. The lander lowers down, starts scanning the ground with radar. Airbags inflate. Rockets ignite and bring it to a stop, and then it cuts the airbag, the whole airbag package, and it falls to the ground. When that happens, those rockets on the rest of the spacecraft, they keep firing, and they fire even harder. And the spacecraft goes up, actually flies into the parachute, hits the parachute, and the two of those fly off, and they crash at a safe distance. They just, we don't try to land them safely. We just want them out of the way, and we just shoot the rocket that way and let it crash, so that we don't risk damaging that rover at all. And then the airbags deflate, the thing opens up, and we've got robots on Mars. All right. Evan's asking, did I see Saturn last night? Yeah, so to the northwest at night, you have this amazing Neowise comet. And over to the south, you've got Jupiter and Saturn, which are super bright in the night sky right now. It's gorgeous. A great time for stargazing and looking at planets and stuff. Ragav is asking, what is the hardest part about landing on Mars? I would say, every stage is really hard. If you mess up at any point of this, it doesn't work. If you don't separate from the cruise stage, you're done. If something happens on entry, let's say your heat shield is cracked or malfunctions, you're done. Let's say your parachute doesn't open, you're done. Let's say the thing isn't able to, extend below the spacecraft, you're done. If the airbags don't inflate, you're done. Everything has to go right. And it all has to go right at the right time. Otherwise, you're done. Okay, so here's what I would say is the hardest part, is making sure all the little details are correct. There was a rover that NASA and the European Space Agency were working on together, and it was supposed to land on Mars in 1998 or 2000, 2002, something like that. And it launched from Earth just fine. It made the journey from Earth to Mars just fine. It went to go land on Mars, and we didn't hear from it. And we're like, what happened? And we eventually, an orbiting satellite around Mars did find it, crashed and burned on the ground. Well, they figured out what happened is we got the math wrong. Someone had done a calculation in the imperial system, so like feet, inches, miles, and someone over in Europe had done the calculation in the metric system, centimeters, meters, kilometers, and so on. And so a number was given from NASA to the European Space Agency, or from the European Space Agency to NASA. And it was like, oh yeah, the number is 10. But they meant 10 kilometers, and these guys thought it meant 10 miles, or these guys said 10 miles, they thought it was 10 kilometers. I don't know what the number was that got confused, but there was a confusion between the imperial system and the metric system. Oops, one calculation was off and the thing crashed. So everyone uses the metric system now. NASA uses kilometers and all that stuff. It's just, it's better to have one language, one system of math that everyone is talking. Okay. All right. Tanisha and Gerard are both asking, which planet would I love to go to the most? Definitely Mars. I would want to go to Mars before anything else. It's the closest. It's right there, right? If you're looking at a tree and there's all these delicious apples on the tree, the first one that you want to pick is the one that you can reach up and grab right now. We are this close to Mars. It is only, 20 light minutes away from us. It's super close. So you got to go there before you go anywhere else. So this landing system, this landing technique is what was used for many, many successful missions, and some unsuccessful ones, but many successful missions. We know it works, we kept using it, but when it came to the Curiosity rover was the size of an SUV. It was the size of a large car. This airbag thing only works for smaller spacecraft, for spacecraft maybe the size of this table or a little bit smaller. The Curiosity rover weighed over a ton. It's still out there. Weighs over a ton. The airbag thing was not going to work. So they had to come up with a new system. And it looks very similar. You're going to see a lot of very familiar parts of it, right? Separates from the cruise stage, enters the atmosphere, slows down, parachute deploys, heat shield separates, it starts using radar, and then things get different. Instead of using an airbag system, they used what we called the sky crane, which sounds awesome, looks even cooler. And here's another photo of it. Instead of lowering down the airbags and then dropping the airbags, this thing is gonna take the rover, lower it down on this crane system, and it's gonna slowly touch it down to the surface of Mars. And then it's gonna separate. It's gonna cut all the cables, and the rocket part of it's gonna fly off and crash at a distance like we talked about. So the whole sequence looks very familiar to the airbag thing, except instead of just throwing a bouncy ball, we need to touch this thing down super gently and super carefully. Well, a bunch of really smart people in the space agencies figured out how to do this. And they called it 7 minutes of terror, because from the moment that you start the landing sequence to the moment that it touches down on Mars, it takes 7 minutes. I'm going to adjust some settings here. I'm going to shut the Q&A window for the moment, and then I'm going to come back to it. This video is about 3.5 minutes, and it's from NASA engineers explaining the entire process of what it's going to take to land this Curiosity rover on the surface of Mars. Give me just a moment here to make sure all the settings are correct. Okay, here we go. Let me know if you can't hear this. I am going to keep the Q&A section open, so let me know if you cannot hear it.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we had never attempted on Mars.
Mars is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater, right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the sky crane maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long, and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage, it's in a collision course with the rover. You must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
Okie doke. So I know that probably looked, you probably didn't have excellent frame rates while watching that video. I'm aware that that's a side effect of showing a video through the webinar here, but I love that video. It does a really great job of showing every step, every stage, the challenges with every single stage. That was video put together by NASA before this thing landed in 2012. And so again, as he said in the video, we're like 14, at the best, we're like 14 minutes away from Mars in terms of the speed of light. So from the beginning of that whole process of landing, to the time that it lands, it takes 7 minutes, and it takes 14 minutes for us to even know that the process has begun. So what it's doing is it's programmed to send tones. It's just a certain beep, a certain note that it beeps back to Earth that tells us, and it beeps each time it hits a certain milestone, a certain waypoint in the process. So every time that the engineers hear the next beep, they go nuts. They're super happy and cheering because it means that this thing, there's nothing they can do. Their jobs are done by this point. All they can do is just sit there and pray and hope that they got all the details right. Because if not, it's going to crash. There is one more video that I want to share here. It's much shorter. Nope, not this one. Go away. There we go. This one's quite a bit shorter. And this is a clip from Mission Control for the Curiosity team as they were sitting there holding their breath, waiting for the news that this thing has come in and landed successfully. And you will know the moment that they get the final news that this thing has successfully landed. All right, I'm gonna make sure my settings are correct here. Good. All right, here we go.
Good job, telemetry. UHF stable. UHF is good. Touchdown confirmed. We're safe on Mars. Time to see where our curiosity will take us.
That's just lovely. I love that clip. I can't tell you how many times I've probably watched that. These men and women have dedicated a good portion of their careers to making sure that this happens. And they've been working on this specific project for probably a good 5 to 10 years. And if it went wrong, they were going to have a bad day. So you can see the relief, the joy, the enthusiasm, the excitement, grown men crying, just hugging everyone around you. Definitely no social distancing happening in 2012. And that kind of reaction is standard for these sorts of missions. High risk, high reward, high cost. And if everything comes out right, you're going to get some amazing science out of it. I think I just have a few more slides here. All right, there we go. You should be able to see my screen again now. So here is a shot from orbit after Curiosity landed. Here is where the Curiosity rover itself was set down. You can see some kind of darker spots there. That's probably dust kicked up from the Sky Crane rocket. You can see the Sky Crane flew off and crashed over there. Some explosion there. Here's the heat shield that landed way over here to the south east. And over here we have the back shell and the parachute, the thing that deployed the Sky Crane and the Curiosity rover. Pretty amazing. So here again is that final diagram showing the entire process. 7 minutes from hitting the atmosphere, from separating from cruise stage and hitting the atmosphere to touching this SUV, the science laboratory, down very gently on the surface of Mars before flying away and crashing crashing the rest of the landing portion there. Yeah, okay, so that is what I have prepared today, which is perfect because we're pretty much out of time here. Gerard's asking, why is the rover called Curiosity? And why is the next one called Perseverance? And before that, they were called Spirit and Opportunity. and Pathfinder and Sojourner. All these names were picked by middle school students. There was a contest that was put around nationally. Any middle school student who wanted to could propose a name, and they would write an essay and give a submission onto the name that they wanted to pick and why they thought. And a panel of engineers and educators at NASA would sit down and look through the submissions, pick out some finalists, and eventually make their decision. So it's called Curiosity because a middle school student who was very passionate about space exploration came up with the name and made a good argument about why we should call it. We are curious. We are fascinated with Mars. Super, super curious. We want to know more. The next one is called Perseverance. As I've talked about in other space science classes, most spacecraft that we send to Mars live a lot longer than we thought or than we initially had our minimal hopes for. Spirit and Opportunity were only supposed to last 90 days. If they lasted 90 days, it was considered mission success. They went for 8 years and 12 years or something like that. They went for years. They were only supposed to last 3 months. Curiosity, if they got 2 good years out of Curiosity, everyone was going to be super happy. It landed 8 years ago and it's still going. Perseverance, they're hoping another 2 years, but they want it to persevere. We could get at least a decade out of Perseverance if everything goes well. So what's it going to take for you to work in the space field? Are you sitting here watching this thinking, I want to go to space, or I want to help build rockets, or I want to help program the rovers? You don't need to be a pilot in order to do this stuff. You need to be good at coding, computer coding. You need to know math. You need to know science. So this is our email address, by the way, onlinelearning@delphian.org. If you have questions, suggestions, a subject that you would like to talk more about, let me know. Heronbooks.com is where you're going to find a ton of curriculum. What I'm teaching out of today is, these are just slides that I put together from my own experience with following space news over the last few years. But the methods that we're using, the approach that I'm taking with this stuff, Heronbooks.com is your resource. You want to go into the field of space exploration, space science, you're going to need a lot of math, a lot of science, other stuff too, but especially those 2 subjects. You can go to heronbooks.com, sort by subject, find something that's at the right age range or grade range for you, and buy the materials there for 10, 15, 20 bucks and continue your education no matter what's happening in the world. I am thrilled that you all have been able to join me today. The last thing I'm going to pull up here, it's called nextrocket.space. I showed this website the other day. This shows what rocket launches are happening coming up soon. We've got Russia and China launching some stuff soon. We got another launch from China coming up. And then let's see who's launching this one. Is that France? I think that's France. And then we've got some SpaceX launches coming up with some more satellites going up. There's a long list here. Every launch off of this planet into space that is known about for the next coming several years, it's all listed here. And it's a lot of fun to just sit and watch this. Thank you for joining me on this journey into space science. Before I leave, I want to ask everyone, what subject would you like to talk about on Thursday? I have not finalized my presentation for Thursday yet. The class is not set. So throw into the Q&A section here, what are you interested in talking about or in learning more about? I'm going to cut the feed here, but I'm going to hang around in the Q&A section for a few minutes and get your input on that. I'll see you in a couple of days.